Chapter 5, Image Reconstruction. First, we'll start with discussing some of the basic principles of image reconstruction. An algorithm is a set of rules or directions for getting a specific output from a specific input. Reconstruction algorithms are used in CT, and they are available as computer software. The Fourier transform, which we've mentioned before, is a mathematical function that converts a signal in the spatial domain to a signal in the frequency domain. And this was developed by a mathematician, Baron Jean-Joseph Fourier, in 1807, and it is used to reconstruct images of patients' anatomy in CT and MRI. Convolution is the digital image processing technique used to modify images through a filter function. Interpolation is the mathematical technique used to estimate the value of a function from known values on either side of the function. This is used in CT and image reconstruction process and determination of slices for spiral and helical imaging. One type of reconstruction algorithm is back projection. Think of 4 beams of X-rays that pass through an unknown object to produce 4 different projection profiles. The problem involves the use of these profiles to reconstruct an image of the unknown object. The projected data sets are back projected to form corresponding images, and then the reconstruction involves summing these back projected images to form an image of the object. I want you to refer to figure 5.6 on page 105 in your book for a picture that lays out the back projection process. This was first used by Oldendorf in 1961 and Kuhl and Edwards in 1963, and it's explained best by the graphical or numerical approach. And the problem with it is that it doesn't produce a sharp image of the object. A star pattern artifact can occur when the points outside a high-density object receive some of the back projected intensity of that object. Iterative algorithms, the primary advantage of them is to reduce the noise and reduce the dose to the patient. They include simultaneous iterative reconstruction techniques and iterative least square techniques and the algebraic reconstruction technique. The algebraic reconstruction technique was first used by Hounsfield in the first brain scanner. In the early CT years, these algorithms weren't used because of limitations, and they're difficult to obtain the accurate X-ray sums because of the quantum noise and also the patient motion. The procedure takes too long to generate the reconstructed image because iteration can be done only after all the projection data sets have been obtained, and due to the lack of computing power to solve the equations quickly. To produce a true image, there should be more projection data sets than pixels, and so this diagnostic projection data sets are taken to eliminate any uncertainty. Iterative algorithms are offered on new scanners by all major CT manufacturers as of 2014. Analytic reconstruction algorithms were developed to overcome limitations of back projection and iterative algorithms used in modern CT scanners. For example, the Fourier transform and the filtered back projection. With the filtered back projection, this is often referred to as the convolution method. The projection profile is filtered or convolved to remove the typical star-like blurring that is known to occur when using the simple back projection technique. So basically, it uses a convolution filter to remove the star-like blurring, which then produces a sharp image. The steps are: the projection profiles are obtained, the logarithm of the data are obtained, the logarithm values are multiplied by a digital filter or convolution filter to generate a set of filtered profiles. Then those filtered profiles are then back projected, and the filtered projections are summed, and the negative and positive components are therefore canceled, which produces an image free of blurring, which is a sharp image. The major problems with the filtered back projection include noise and streak artifact. With Fourier reconstruction, this is used in MRI, but not in modern CT. The spatial domain image is transformed into the frequency domain image by the use of the Fourier transform. The frequency image consists of a range of high to low frequencies, and the frequency image can be retransformed into the spatial domain using the inverse Fourier transform. The Fourier transform does not use any filtering. There are 4 data types, which are measurement data, raw data, filtered raw data, and image data. With measurement data, this arises from the detectors. It's also known as scan data, and it is subject to pre-processing to correct the measurement data before the image reconstruction algorithm is applied. These corrections are necessary because of errors in the measurement data from beam hardening, adjustments for bad detector readings, or scattered radiation. Without the correction of these errors, there will be poor image quality and artifacts will be produced. Raw data is the result of pre-processed scan data and are subjected to the image reconstruction algorithm used by the scanner. This data can be stored and retrieved as needed, whenever necessary. Convolved data, or filtered raw data, improves the image quality through the removal of blur. This uses the convolution kernels, which are only applied to raw data. Image data, also known as reconstructed data, is convolved data that has been back projected into the image matrix to create CT images displayed on a monitor. Various digital filters are always available to suppress noise and improve the detail, such as a standard algorithm, a smoothing algorithm, and an edge enhancement algorithm. With the standard algorithm, this is usually used before previous algorithms. It's used for when a balance of the noise and the detail is necessary. The smoothing algorithm reduces the image noise and shows good soft tissue anatomy. They're used in exams when soft tissue discrimination is important to visualize the very low contrast structures. And edge enhancement algorithms emphasize the edges of structures, as you may have guessed, and improve detail but create image noise. This is used in exams where fine detail is important, like the inner ear, bone structures, and fine pulmonary structures. Multiple slice CT scanning requires new algorithms for image reconstruction than single slice CT scanning uses. These new algorithms are very complex, but we'll discuss them briefly in this chapter and a little bit more in depth later. For a 4-detector row multi-slice CT scanner, the beam divergence from the X-ray tube to the outer edges of the detectors increases, which is called a cone beam. Within the cone beam, the X-rays will be measured by the detectors are tilted at an angle relative to the central plane. This is the plane perpendicular to the long axis of the patient, which is the z-axis. As the detector rows increase, the cone angle becomes larger. The larger cone angles cause problems because beam divergence along the z-axis becomes greater. And this produces inconsistent data since the plane of interest is being projected onto several detector rows. And this leads to streaking and density changes. The cone beam algorithm was developed to eliminate cone beam artifacts that we just mentioned. And one example of a cone beam algorithm is the adaptive multiple plane reconstruction algorithm.